after some time, we are back with the seminars, and we are very happy, and we really thank Ioan and Laurent for being here today and to give a presentation. It's not easy to find speakers, so it's very difficult to continue to do seminars. So we are really happy today that we can have another round of the seminar. So this is a nice invitation to everyone to show up in case they want to present their data research or they have something related to speech translation, not only speech translation. This is the right place for advertise their work. So today the speaker are Ioan Calapodescu, Senior Scientist at Naver Labs Europe and the NLP team, and Laurent Besacier, Principal Scientist at Naver Labs Europe, and he's leading the Interactive System Group. So they will talk about the recent work on speech translation at Naver Labs Europe. So first of all, we want to thank the speaker for being here today, and it's great to have you guys. And yeah, so the floor is yours. Do you want to have the question at the end, or you can be interrupted over your presentation, please?
Personally, I don't mind. If you have question, you can just interrupt me and ask away.
Same for me.
Great. Thank you. Ioan, the stage is yours. Thanks a lot for being here.
Thank you, Marco. Hi, everyone. Thank you for coming. My name is Ioan, as Marco said, and my talk is about multimodal machine translation for speech and text. And basically, this presentation is to introduce some work we did basically at Naver Labs Europe, or NLE in short, since last year when we started to work on speech translation. The team had a lot of experience working on machine translation, but text only. And we decided to start working on speech translation. And to make our life more difficult, we decided to make it multimodal machine translation. And basically, what we wanted to design is a multimodal model, which means that we want to do both inside the same model, speech and text to text translation. And we started last year by trying to find a design for this kind of model that allows to translate two modalities. And we did some preliminary experiments on multilingual TEDx as a setting. And from this very first experiments, we applied this architecture on some low resource settings to see if it still works, like translating Tamacek to French. And the last part of my presentation will be actually about IWSLT because we participated to the dialect and low resource track. Basically, we submitted the results somewhere last week, I think, and just today we submitted the first draft of the paper a few hours ago. So it's just some highlights of the paper you will see soon. And I have also some results to share about high resource settings because our model kind of works in different settings. So let's look at our very basic experiments on speech translation because we were basically learning to do that. And we decided to work on MTEDx, the multilingual TEDx dataset. It was a very nice setting for us because it's multilingual, and it's multimodal. And so we have different tasks also that we may want to do, translating the audio, translating the transcription, doing the transcriptions, and all these tasks in different languages. So we took that as a first data set. And we wanted to do multimodal machine translation, and I want to insist a little on what I mean by that. So you all know the basic pipeline, for example, model to do speech translation, where you can use an ASR system and then use an empty text-to-text system to translate your audio. You all know the end-to-end approaches to do the same thing, where you have some kind of encoding of the speech and some kind of decoder that decode text, and you have an end-to-end speech-to-text system. But what we wanted to do, for scalability reasons and for fun, was something a little different. We wanted to be able to translate both actually inside the same model. And for us, it was really a strong constraint that we imposed on ourselves. So while I mainly present speech translation results, and you will understand why in a moment, actually all the models that I will present and architectures have this main core ability to be able to translate both and text and speech, so that when we deploy machine translation technologies at Naver, for example, we can use a single GPU to do all these things instead of several, and hopefully perhaps even improve the results. But before doing that, we had to build our first pipelines and models and tests to see how it actually works, because as I said, it was relatively new for us, the speech part. And the basic kind of architecture, as I said, you have some kind of speech encoder that can have various settings. You can have some feature extractor based on MFCC, on Web2Vec, on various pre-trained models. And you may have different other modules on top as an encoder system that kind of looks like that. So you put your speech in input and you have some speech representation system that deal with that. And you have many variations around that. Some using pre-trained models, some are not, but it kind of looks like that. And on the other part, for the decoder, you have some kind of text decoder that generates the translation. And again, it can be randomly initialized. It can be initialized for an existing machine translation system, embodied model or whatever, right? And so we implemented this kind of baseline ourselves just to see how it works and to get us started on the problem. And we trained that on MTEDx with all the data we had, so 2000 sentences. And we also did a training of this kind of architecture on speech translation and ASR at the same time to see if it actually helps the translation. And this experiment really was for us just to compare, to have the baselines going and to understand the system, have text-to-text, the pipeline system, the speech-to-text. And we used very basic models. For example, for the pipeline, we used SpeechBrain, off-the-shelf ASR system, things like that. We trained this very simple architecture I showed you that you can find similar implementations, for example, in FairSec if you want to test it for yourself. And we train it on speech translation and ASR on this data set. And for extracting the features, we use XLSR 53 because it was multilingual representation of audio. And for the transformer base for the text-to-text and small for the speech-to-text system, simply because even on 2000 sentences, we had some kind of overfitting problems with bigger models. And here are this very first table of results. In blue, you have the text-to-text model working on Oracle transcriptions. And basically, the Oracle translation is the best one in this system. It works quite well. More strangely, the pipeline and the end-to-end system are relatively close, but mainly because our ASR off-the-shelf system was not great, actually, and was not very adapted to multilingual TEDx. So we have very similar results. And more troubling is that actually adding this ASR data in yellow here doesn't actually help at all. So even if we double the amount of speech and text the system sees, it doesn't really help on this very simple architecture. But at least we had our setting going, because what we want to do, again, it's a multi-modal model, something that will be able to do both. So the same thing as the blue line and the same thing as the other experiments. And hopefully, actually something better that will be here in the middle. And we decided to do that by trying to composing these two architectures together, the text-to-text model and the speech-to-text architecture. And to do that, we first started to train our own MT system, just a basic text-to-text model that was trained, so encoder, decoder, that was trained with the Oracle transcriptions and the translations, but also with a strange copy task for copying, for example, French to French. So that's basically our text-to-text model, and we know that it's the best we can have. It's a blue score that we saw in the previous slide. So when we want to add text, we will stack something around speech, but we load this model and we completely freeze it. We don't want to modify it because we want to keep all the capabilities of this blue line. We don't want to degrade the results. So everything is frozen on the text-to-text part.
Sorry, just
Yeah.
a curiosity. Did you frozen both the encoder and the decoder, or only the
Everything.
decoder? Everything. Okay. And when you use the copy mechanism, does it help the translation? So you translate from English to French and you add the copying, the French to French. Does it help somehow?
Yes, actually it helps somehow.
Okay, thanks.
This
Maybe
time, and you will see it on the next slides.
Exactly, I didn't want to spoil it, sorry.
And basically, to plug these two models, we just add a few transformer layers at the bottom of the encoder. So we add just like one or two transformer layers, very simple, with some convolution layer. And we add the wave-to-vec model, the speech representation model, even on the bottom. And this one also, we completely freeze it. So basically, the only thing that is trained is these 2-3 layers. We just add a few adapters on the encoder decoder side of the text model. And you will see later why they are useful, but the system works also without them. And to train it, we just put speech inside, and we put speech and translation and speech and transcriptions. It's why we added this copy mechanism, and it actually helps. And just to evaluate that, basically, you can, with this architecture, you can do text-to-text MT. You put your input here on the first text layer. You can put speech at the bottom, and depending on the language codes, the task becomes MT or ASR, right? So very simple kind of architecture we wanted to test. And I just want to highlight that a very fundamental difference with other stacking strategies, because if you are familiar with the domain, you know that people tried different ways of stacking these things, is that really in this one, we freeze everything else and nothing is modified. And basically we train only these glue layers in the middle, which means that fundamentally when we train with our cross entropy, even if it's a translation task, what this layer learn, they are not learning to do translation. They are just learning to project speech representation into an abstract other space, another embedding space, which is an embedding space from the text-to-text MT system. And so we tested that, and these are the results. And we tested it so in two, so the gray and yellow lines are the ones you saw before, and the blue and green are the stacked model. And it works a little better than by actually several blue points in average than the previous system. And this time, contrary to the first experiment, adding the ASR data adds a few blue points more. But we are still kind of far from the end to the Oracle text-to-text translation. But still, it's an improvement. And so, as I said, it kind of works. It works a little better than the speech-only encoder thing. This time, the ASR task seems to help a little. I guess it's just because it sees more data, and again, it works better because we added also this fake copy task at the beginning for the text-to-text model. And it's also more stable. For example, we were able to increase the capacity of the model while before we had a very small capacity for the speech-to-text system. And so we have this. We had this very first experiment to play with multimodal translation. It seems to kind of work, but still a lot of limitations. For example, we don't know if it's actually if we compare it to the state of the art, like for example, the first submission at IWSLT 2021 on multilingual MT with, again, some kind of stacked system, but trained very differently. We don't know if it's competitive. And we don't know either at that point if it's working on different settings like low resource settings. And actually, it's the second options we choose to explore first. See if this kind of preliminary results actually works if we test it on very low resource settings. And we tested that on Tamachek. And we tried to, with this architecture, to do translation of Tamachek, which is an African language in the Berber family, spoken in all these countries. And the dataset contains radio recordings from daily broadcasts from two sources, and we have only speech translation, so speech on one side in Tamachek and translation in French. And we have 5,000 lines, 17 hours of data. And we have also some kind of raw data with no transcription, no nothing in Tamachek, in French, and some other local dialects that were available to use. And we use this data in our system. So this time we switched to pre-trained models. We didn't train our own text-to-text model. We took embodied or NLB, so that people can also reproduce more easily these kind of experiments. And for the speech representation, we use two settings. The first one using XLSR, pre-trained, and another using Hubert, but that we train ourselves with additional Tamachek data, for example, or Berber languages. And this is a table of results. So on the top, this is our different experiments. On the bottom, you have the baselines we are comparing to. The first one is a baseline proposed in the paper that actually presented the dataset. And the second one, second results were presented actually last year, summer last year at GSALT workshop. A few observations. So the architecture seems to work also relatively nicely in this low resource setting, where a pipeline model is not even usable. It seems to work better than the very basic baseline proposed at IWSLT 2022, and better than this state of the art we have found at GSALT, while using actually relatively few parameters and a lot less data than in this experiment, for example, which is some interesting results. And based on these results, we saw that IWSLT is very busy on adding new tasks and challenges. And this year they added a few other challenges for us. So not only Tamachek, but Quechua and other languages. And we participated to the task in these two, with these two language pairs, Tamachek to French and Quechua to Spanish. And for the data and the pre-trained models, so for Quechua, there is even less translation data than we had for Tamachek, only 2 hours and something. But there is some ASR data that we can use to help us. And in addition to that, we also used for the target languages some other sources of audio, like English, French, Spanish, etc. So we are in unconstrained mode. And for the pre-trained model, again, we reused XLSR53, but also XLS-R. They try to make our life difficult with these names. And also our own pre-trained model that I presented previously. I'm Hubert, Tamacek, and two other pre-trained models that were trained by Marceli and O. And for the architecture, is actually pretty similar to the first one I showed. So in blue here, light blue, you have the text-to-text model that is frozen. So we can input text in here. And the glue layers here, the difference with our first experiment is that instead of starting with initially randomly initialized layers, we actually take the three first layers from the text-to-text model and we fine-tune them, only them, for speech. So we make a copy, and one of the copies we fine-tune it on speech, while we keep the other frozen for text, and we still have the both capabilities of translating text and speech.
Sorry,
but everything else is similar.
Sorry, I have a question, Ioan. But do you have more data for text than for speech in this case? So for building the text-to-text, do you have more data than for building the
actually, we
speech-to-text?
used, again, the same kind of setting as previously. We use pre-trained embodied and pre-trained NLLB systems. Okay. So people can easily, yeah.
No, but I was wondering if you can alternate. You can first froze the text, train the audio, and then froze the audio and try to have another kind of tuning of the text, if it can help somehow.
Actually, at my very last slide, I have some nice observation about this.
Sorry.
These adapter layers that did something a little strange that we were not expected to see. And it's related to your question.
Okay.
And so, yeah, basically, we tested this variation of the architecture, but also the other one that works actually quite well too. And these are the preliminary results. The official results are not there yet. The organizer will share them when they are ready. But they already shared our own bleu scores on this data. And for Tamacek to French, we have a bleu score in the 20s, which is way better than what we had before. And also on Quechua Spanish, we have relatively good results in 17 points of bleu. And while we don't have the official results, if my understanding is correct, of our discussion with organizers, it seems that these two models, our two participation ranked actually very probably first for both tasks. But we'll wait for the official results to confirm that. So very, a priori, very good results for this low resource setting on Tamacek, but also on Quechua. And at that point, we also tested it actually on high resource languages. One of our objectives was to see if we can compare to IWSLT 2021 with this FAIR model that was really huge and also stacking, but differently. And we compared our settings, but training it with IWSLT data. And here are our results. As you can see, we are actually very competitive for the main training direction. So we have better scores with our settings on all the four language pairs where we have training data in MTEDx. But with the advantage that this model, while bigger, it's way less expensive to train. For example, our model takes 46 hours to train on 4 B100, which means that if we have 8 GPUs, it's less than 24 hours. While it takes 7 full days of computation for these models to actually train. So it's relatively interesting for us. And for the zero shot direction, actually, as you can see, we have relatively comparable results, but we are slightly below. But mainly because we decided to make our life a little harder, again, by not using any training data in these language pairs. So basically, our model was trained never saw Portuguese to Spanish speech-to-text translation data, which was not the case for FAIR submission. FAIR submission had seen these languages for speech-to-text, but not in the MTDX settings. And we hope to have the time to complete some experiments and have more comparisons between these two models. Just for the last 2 minutes, on my part, just some interesting informations. So the model is really nice. It seems some very nice capabilities in true zero shot translation system, meaning that here you have a few examples where we tested. You see the reference or output in French, but we can directly ask the system to translate in English or even in Korean, and it seems to actually work very nicely. So if tomorrow somebody asks me to do I don't know, Tamachek to Chinese MT system, I can tell him or her that I just need 10 hours of Tamachek to French to make that working, which is kind of nice. And the other nice observation, Marco, to answer to your previous question. So the model is still a text-to-text model, right? So our text-to-text is completely frozen. And it's good, but it's actually better after our training. So basically, we adapted it through speech. Let me go back to the figure. So basically, everything is frozen, and we have a first step training with speech, right? And during this training, only these layers are trained and these small adapters. And we evaluate with speech. We have some good results. We're happy with that. But then we evaluate on text. And we evaluate on text on MTDX data. But this time we keep the adapters here. And these adapters saw some speech. And this time our results are 2.7 bleu more. So basically we adapted a text-to-text model by feeding it some speech data. In the paper, we will have comparison by fine-tuning the text-to-text only, which works a little better. But 2.7 bleu score are interesting. So that's nice. It's something we want to look a little more at. And there will be more details in the paper. We have 50 pages of tables, ablation study, and other stuff if you are interested.
It's very interesting, this part, that because this is very multimodal. You are learning from audio to improve machine translation. That's very interesting, very nice.
Yeah, and so it works really both ways, right? Basically, the speech translation system is actually good because we have a huge text-to-text model on top. So it was expected, but as you said, it also works in the other direction, and it's it's kind of cool. And there is other small thing we want to investigate. Basically, this frozen architecture, as I mentioned, it even works without the adapters, right? That are just doing some kind of basic domain adaptation, which means that we are learning this projection system of the wave-to-vec embedding space to whatever embedding space was in the empty system. So we can imagine if we take these embeddings created by the system and we try to find back the BPs, you know, to recreate a text. For example, for French, it will look like French. It's a good guess, right? But what will be the output of this test for Tamacek? What kind of transcription the model did create itself so it can translate Tamacek? That's a question I have no answer to, but I want to look into it. Yeah, that's it for me. Wow.
Very interesting. Thanks, Ioan. Do you have any question for Ioan? So don't be shy. I mean, yeah, it's very informal seminar, so don't worry. Okay, so I think we can move to Laurent. Thanks a lot, Ioan.
Thank you.
Thanks, Ioan. Let me share my screen. And my presentation should be shorter because it's a more preliminary project we did. Let me. Okay, let me go full screen. Okay, can you see it?
Yes, we can see everything. Thanks.
Okay, so this is a project about building a metric for speech-to-speech comparison. And basically, the idea started when we participated to GSALT 2022 last year. Ioan and myself, we were involved in this group working on speech-to-speech translation for low-resource languages. And among the low-resource languages were the Tamacek that was already mentioned by Ioan. And when you do speech-to-speech in that direction, then the question is, how are you going to evaluate the quality of the speech that is generated, especially because you don't have a very good ASR system for Tamacek, or maybe you don't even have an ASR system for Tamacek, and so you cannot rely on the basic approach, which consists in doing what we call ASR bleu, where basically you will retranscribe the speech output into a text and then compute bleu from this. So this was really a preliminary work on building a speech-to-speech comparison metric. And this is not only Ioan and myself, but we work with Olivier and Sven from LNE, which is Laboratoire National d'Essai. And well, to make it short, it's something comparable to NIST, but in Paris, in France. So let me explain what we did during the project, and there is a paper on archive at the moment that describes this if you're interested. So the goal was really to build a metric that is textless, that is based on audio only, and basically we would like to be able to, let's say that you're doing speech-to-speech translation, you have a reference audio and a generated audio by your system, and you want to be able to provide a score that compares these two. And you want this score, which is speech-based, that is, you want it to be highly correlated with the equivalent score that you would have if you were working on the text transcripts of these audio signals. So basically, we wanted to build a textless metric that has a strong correlation with the same similarity metric that will be applied to the same pair of signals, but on their transcripts, basically. And so in this work, we really wanted to check that the meaning is preserved, is the same, but you can imagine working on other axes, for instance, comparing with the framework we propose, we could work also on having high similarity if the voices of the speakers are similar, for instance. But for the moment, we really worked on the meaning. So why would we like to do that? So as I said already, to evaluate a speech-to-speech translation system without falling back to a transcription of the hypothesis and reference when we do speech-to-speech. And also because for some languages, so so this first bullet point is meaningful, whatever the target language is, but it is even more relevant for some languages like Tamashek, where maybe it's difficult to fall back to a transcription simply because there is no transcription, or there is no transcription system, or the transcription system is too weak. And we didn't address this, but in the future, having such a metric could help for hyperparameter tuning, or even using this as a training objective for building end-to-end speech-to-speech translation systems. So we started with a very simple approach, which consists in reusing the existing text metrics on speech units that are extracted from the speech signal. And you know that with models such as Hubert, it's possible to extract discrete speech units. So the first very straightforward approach was to say, okay, let's reuse our existing text metric, but apply them on some discrete acoustic units that we can extract from the signal. And the second approach was a bit more complex. It was to use a metric learning framework to predict a score between an audio reference and audio hypothesis. And we would train these scores to be very similar to the text-based counterpart. And so the spoiler is that the first naive approach doesn't work at all. So I'm going to go very fast over it. But the second approach, we demonstrated that it works on both synthetic and natural pairs of speech utterances. And we did experiment for English as a target language only for the moment. So this is still has to be confirmed in a multilingual setting. This is why I said in the introduction that this is a preliminary work. So let's go very fast over the naive approach, which doesn't work again. So let's say that you want to compare an audio hypothesis H and an audio reference R. You can come up with some kind of discrete acoustic units. So what we did as this basic experiment, we used MFCCs to extract MFCCs, and then we quantize those MFCCs representation in order to have a code book, and so convert them into like discrete acoustic units. And we did deduplication, which consists in when you have like a sequence of similar units, you just keep a single one. So this is what deduplication is. And then, since we are back to some sort of discrete sequences, we can use our preferred metric, whether it is BLEU or CHRF or whatever. So we did a quick experiment. So in order to set up some experimental framework for this, what we did is that we use Common Voice as a starting point. Common Voice is a very large collection of read speech by multiple speakers. And so basically we selected 20 million of pairs of utterances, which had at least 1 4 gram in common, so that we can have the full range. So we have pairs which are very similar and pairs which are very dissimilar. And this was a very simple way to select a collection of speech pairs which had a BLEU score when we were comparing them that ranged from 0 to 1 BLEU, basically. We had the full range, right? And so we took a subset of this, and we built some scatter plots where we basically computed the text-based BLEU score on the x-axis and the speech-based BLEU score on the y-axis to see if there is some kind of correlation. And I said that there is no correlation if you apply this very basic approach. So on those different scatter plots, you have the text BLEU on the x-axis and the speech BLEU on the y-axis, and this is done with different sizes of code books for the MFCCs. But whatever you are doing, you would expect to have like some kind of correlation, but there is no correlation here. So let me go very fast over this. So this is the first lesson. So it's a failure. And basically, we decided that we need to change two things in our approach. The first thing is to use, instead of using those very local acoustic features, which are MFCC, try to use more contextualized features such as Hubert representations, which are units that we know convey more contextualized and more semantic speech information, as this is shown in the Superg benchmark, for instance. Using Hubert representation can lead to a very good result in different tasks, and not only ASR, but also classification tasks. And second thing we changed is that we moved from unsupervised metrics such as BLEU or CHRF to learned metrics, basically. So we come up with this architecture, which is basically the main contribution of this project, which consists in learning a metric. So let me explain what it does. So we still want to compute a score between audio hypothesis H and audio reference R. We are going to convert this into discrete acoustic units using Hubert, for instance. And then we are going to encode somehow the sequence of discrete acoustic units. And for this, as an encoder, because we just need a text encoder for doing this, so we used XLM Roberta. And then once we have like a latent representation of the hypothesis and the reference, we are going to pull this and add a regression layer on top of it in order to predict a score that we call this speech here. And we want this score to be very similar to the text-based counterpart of the scores that you can obtain if you take the true transcript of H and the true transcript of R and you compute it. So this is a regression task, and the training parameter of this are going to be the parameter of the feed-forward layer, but also the parameter of XLM Roberta. And if you look at this architecture, actually, there is an already existing framework for doing it, which is Comet, basically. So if you look at Comet, this is not only a metric, but this is really a framework for building metric. The difference is that when people are using Comet, they try to have a good correlation with human judgment. So basically, instead of having this text here, you have a human judgment, which is basically a score, and you try to build an architecture that will predict as much as possible this score. What we do in our case is to predict the text-based counterpart of the metric. And we have a lot of data for that, because as you have seen, just taking, for instance, our 20 million of common voice pairs of utterances, we can do that because we range the full, we can cover the full range of BLEU values. So this is basically what we did. So let me go very quickly over the results. First, we experimented on some synthetic speech. And for this, we used the CVSS, so this is Common Voice Speech-to-Speech corpus. So basically, we did a few manipulations. So we end up with some train, dev, and test set that basically cover a pair of utterances that corresponds to different speakers with different value. So here, we try to predict CHRF. And you can see that we have similar utterances in our distribution of pairs of utterances. So these are the ones that lead to very high CHRF score when we compare them. And we have some more dissimilar or even very dissimilar pair of utterances. And so we just use a subset of CVSS for this. And we started from this from a data set that has this distribution. So this is distribution of the test set, but we had a training set and a dev set that have similar distribution. So basically, from this, we can build a CRF baseline, a CHRF baseline that consists in just the naive approach I mentioned, but instead of using quantized MFCC, we are using Hubert. So we will see the performance of this naive baseline. And then we learn our metric on different amount of training data. And let me show you the result. And let me explain basically this table, because there are several features that are involved here. So the first line is, okay, we build CHRF, okay, so this is a not learned approach. CHRF, you just compare sequences. So this will be, we will compare our metric and we compute the correlation between our metric and this basic CHRF, because we have access to the transcript of our pairs of utterances. And now, just to verify that the framework is working well, because we were using the Comet framework for doing this, if we forget about the speech input, what we can do is try to mimic the behavior of CHRF by learning a metric that will use the text, encode it with XLM Roberta, and for instance, use some training data like 15,000 utterances, train the metric based on this. And yes, it's just a sanity check, but yes, using the Comet framework, we can learn a metric that is very highly correlated with the CHRF. But this is considered as a top line here because we are using text input. Okay. So now let's move to audio input. And so we have an additional baseline, which is a naive one. This is the same as the one I presented earlier with MFCC, which was bad. The only difference is that instead of using quantized MFCC, now we are using we are using Hubert discrete units, and we decided to go for a vocabulary of 50 different acoustic units. And so you see that this is not a very good baseline. So correlation is positive, but Pearson and Spearman that are around 0.4 are not very good correlation. Okay. And so now all the other lines are going to be the metrics that has been learned using our framework with different amount of training data from 15,000 utterances to 200,000 utterances, with different number of Hubert units in terms of discrete acoustic unit vocabulary, and with different number of epochs. And what we see is that by training longer with more data, again, this is synthetic speech, using our architecture, basically we don't reach the top line, of course, which is based on text, but we can get some quite better correlations. So now the question is, what does that mean to have like a correlation coefficient that is almost 0.8? So let me show you, for instance, the distribution of our CHRF score. So on the left part, you have the true distribution. So when we compute CHRF from the text transcripts, so you can see the true distribution on our test set here. And what you can see here is the estimated distribution when we pull the data all together of using our learned metric. So you can see that, not surprisingly, when learning, the model is learning also to reproduce the same distribution of scores it has seen during training. But it doesn't mean that the scores are exactly the same between speech and text. So you have seen the correlation. 0.8 is not that good, right?
I have a question, Laurent.
Yeah.
How the distribution affect the prediction capability of the system? I mean, I remember when I was on quality estimation, if you have a distribution like the one on the left, the system tend to predict more close. So it's very good in predicting high CRF, but very poor in predicting low CRF. Is this the same here?
Yes. So we didn't deeply investigate this thing, but we will see the next result with natural speech with a completely different distribution. And yes, it shows that if you have too many, for instance, very similar utterances, the model will learn to predict them because, but what we try to do is here to balance. If you look at the area under this distribution, we try to have like a similar amount of highly similar utterances and also pairs that are dissimilar with different degree of dissimilarity. But yes, the distribution will definitely impact because somehow the model is going to learn to reproduce this distribution at some point. So let me go for the remaining 5 minutes to go over the natural speech experiments, because what I just presented was done on synthetic speech with different speaker voices, but still it was synthetic speech. So we reused our natural common voice corpus, where we selected those pairs of utterances. So the hypotheses and reference are natural speech. They are from different speakers. And again, they correspond to similar or slightly dissimilar or very dissimilar transcripts. So you have here the bleu distribution on our test again. You see that bleu so the utterances can be very similar. And we have also very dissimilar utterances, and we have a bunch of utterances that are in between. This is, and since it is more tricky to learn on natural speech, of course. So basically, we use a much bigger training set of almost 1 million pairs of utterances, and we use 5,000 for dev and for test. So let me go directly to the result. The same architecture was used. Let me show you first the loss curve, for instance, when we train on this almost 1 million of pairs of utterances. I want to show the loss curve because so it's again it's a regression task, right? So the loss is basically the mean square error, and you can see here. I would like to explain this drop that we have here in the loss curve here is because in the default setting of Comet, what is happening is that we start by first only learning the parameters of the regression part, but the Roberta encoder, which encode basically the sequence, is kept frozen. And after 1/3 of the first epoch, we are going to start also updating the parameter of the Roberta encoder, which encodes the sequences. And you can see exactly this part is really at the 1/3 of the first epoch. We start that we see that and this is the basic setting. I don't know exactly what it's like, why it's like this in Comet. Probably because they noticed that it was useful to start by freezing the sequence encoder and just learning the regression, and then start to learning everything. But we keep this setting similar, and we can really observe that after we start also learning the parameter of Roberta, we see this loss decreasing here. And so let's look at the results, but we wanted to have some baselines. And there is interesting finding about the baseline, and I will finish with this basically. So we had our dev and test set. We still compute the correlation between our metric score predicted and the text-based counterpart of the score. And this time we were trying to predict a speech bleu to be compared with the text bleu. And you can see that we had much more, even if the data was natural speech, we have much more training data, almost 1 million pairs here. So the correlation coefficients are quite high, but again, it's always very difficult to know what those means, what those correlation means. So we basically compared with the baseline, that is basically what is used when people do speech-to-speech translation evaluation. They are using this ASR bleu, which basically consists in taking your audio hypothesis and your audio reference, take an ASR system in the target language, transcribe, and then compute the bleu between the two transcriptions. Or actually, basically, you can compute the bleu between the transcription of the hypothesis and the reference of the reference. What we did is we used two different ASR systems for this. In order to show the impact also of the quality of the ASR system, because remember, originally we were planning to work on low resource languages such as Tamacek that are not necessarily equipped with very strong ASR system. So we use Whisper-Tiny, which report a word error rate of 28.8% on common voice, and Whisper Large, which report a much lower word error rate. And you can see that the correlation coefficient, when you use this ASR bleu baseline as a metric, are quite poor actually. So of course it improves if the ASR system is getting better, but I think it's important the first finding of this is that, okay, using this ASR bleu can be dangerous if you rely on an ASR system that is not very good. And this is basically what people are doing when the target language is something different than English and French. So care should be taken on using the ASR bleu metric when you do a speech-to-speech translation evaluation, especially if the ASR system is not very good, as we can see here. And even when the ASR system is better, like Whisper Large, we can all agree that this is a very good ASR system, even for English. And still, by learning our metric, we get a slightly better correlation coefficient. So let me skip to, I wanted to make you here to some audio examples for single utterances, but we can do it later if you want. And this is a recent audio supplementary material that I prepared, and I will probably append it to an update of the archive paper we have. But to conclude on this, before taking some questions, so yes, there is enough information in a sequence of discrete Hubert units to score the semantic similarity between an audio hypothesis and an audio reference, even if the speaker voices differ. But a proper learning metric or learning framework is needed to increase the correlation with a text-based score. And another side finding, basically, is that in situations where the target language lacks a robust ASR system, relying solely on the ASR bleu, which is now a standard in speech-to-speech translation evaluation, could be misleading, according to our finding. So the next step is to check that we can learn this metric in a multilingual setting with multilingual data and generalize to new unseen languages. We know that Comet is able to do it. So a Comet metric can we learn from multilingual data and being applied to new language, and it works if we have an encoder for all these languages, and we have multilingual encoder in text, but we also have multilingual encoder in speech. So it should work in theory, but it has to be checked. And also the metric or the framework could be used for other stuff. So for instance, I was very interested at the last Interspeech 2022. There was this MOS prediction task in TTS, where people were trying to learn a metric that will correlate well with the mean opinion score that is used in TTS evaluation. So probably our framework could be adapted for doing this as well. Sorry, I was a bit long, but maybe I prefer to take some question. And if there is no question, we can listen to some audio examples or whatever you would like.
Thanks a lot, Laurent. Don't worry about the time. I mean, everyone can, if it's too late for them, they can decide to quick. Don't worry about it. So I have a question. So, and then we can listen the example.
Yes, sure.
So speech is richer than text. So in speech, you have much more information. So what your metric is going to catch? Just to give an example, if you have two people with very similar or the same person with very strong accent that pronounce two different sentences, it will score low or high, and vice versa. Two people with very different accent pronounce the same sentence. So my question is going to catch the semantic, the meaning of the sentence, or additional aspect that can be accents or something like that?
Yeah, so the way the metric is trained, it's really to catch the semantics, the similarity of the utterances. So my guess is that the metric is learning to remove, for instance, the speaker information, because basically, and I will show you on some example, if we have like different speaker voices, but the same content, the metric will utter a score, will provide a score that is a bleu of 1, for instance, or near 1. So okay. The way the metric is learned, it is learned to correlate with the text-based counterpart. So if the utterances are dissimilar, it will output a low score, and if they are similar, it output a high bleu score, for instance. So it will learn to forget about the speaker information. But it's just because this is the way we learn the metric. We learn it to correlate with the text-based, but we could have anything else here, I guess.
Very interesting, very interesting. It can be also used for cleaning speech-to-speech data when you make it multilingual.
Yeah, but we need to check that it works multilingually. So I don't know if I
There
can
is another
maybe...
question by
Yeah, sure.
Luan
Yes.
before going to listen to the sample. Luan?
Excuse me. Can you hear me?
Yes, I can.
Very well.
Thank you for your presentation, and I just want to ask you for some questions like, if I want to evaluate my translation model with use the same target language like English, and what should I do? It's like, will I use the same model? I mean, the trend model from your project, or should I fine tune it or something?
Yeah, so I guess that if you are like in the... So there is, of course, as in for any domain, for any models, there is a domain that is important. And for instance, this model was trained on English for English, but on the common voice data. So this is rate speech. I think this metric can provide decent score when you compare utterances that are in English and that are correspond to similar settings as common voice. Probably if you are going to a very different domain, or if you want to use like telephone data, like this switchboard corpus, probably you're going to have you are going to have a decrease in terms of correlation, because probably this metric will have to be adapted to a more domain specific setting. But like always, right? But yeah, so that's my answer.
Yeah, thank you so much. And I just want to ask, like, as you mentioned in encoding layers, something like a speech to unique Hubert, I'm not sure that if we apply to some reading, I mean, of some untranscribed languages, and there are some phonics so different from English. So do we have to use another, I mean, something like train another Hubert for that?
Yes, so that's a very good point. So at the moment, if you look at, for instance, a Geekfest platform, you have a Hubert model for English. On our side, we are working on maybe some more multilingual versions of it. And by the way, there are also some multilingual versions that were out recently by trained by people from Meta, I think. But yes, probably having I guess that you can obtain already decent result with English Hubert, because probably even if the language is different, it will extract some. If you allow enough units, like maybe more than 200, maybe the model will extract meaningful units, even if the model was trained on English. But definitely having a multilingual version of such Hubert is interesting. And I mean, you could also like replace this Hubert plus XLM Roberta by something different, like a Wave2Vec multilingual XLSR 53 model, and have some latent representation here. It's just that we wanted to reuse the Comet framework, and it was much quick to actually take the Comet framework and just had this Hubert layer before it. It was basically stacked before the rest of the Comet framework, that is remaining the same, rather than starting from a true speech encoder and completely change the code of Comet to actually build this. But we basically are having these two Hubert followed by XLM Roberta for sequence encoding. It seems to be powerful already.
Yeah, thank you so much for answer.
For people who are interested, maybe I can take 2 minutes just to show some example. I'm going to do the sharing and share the audio as well. And I'm going to share this very quickly. Okay. Can you see my screen?
Yes.
Okay, so it's a very simple example. We randomly selected some pairs of iterances that you can see here, file 1, file 2, and in the first column we show the text-based bleu. In the second column we show the speech bleu that was predicted by our system, and in the last two columns this is the SR bleu baseline we using Whisper Tiny or Whisper Large. And let me start by taking two similar iterances, so similar content but different speakers, so we can listen to them.
From that day on, it was the desert that would be important.
Okay, and the second iterance is the same but different speaker.
From that day on, it was the desert that would be important.
So you can hear that the content is the same, but speakers are different. Because of the SR errors, Whisper Tiny will not provide a maximum bleu score of 1, whereas Whisper Large will, and our metric will as well. Let's take now some a bit more dissimilar iterances, like for instance these two.
This loan was extended until the end of the season.
And this second one here.
He was sacked at the end of the season.
So you can hear that the beginning of the iterances is different, but at the end we have at the end of the season. So there are like common n-grams. And so the text-based bleu is this value, so 41.8. You see that our prediction is not super precise. This is 31 here, but nor is the prediction of the SR bleu using Whisper Tiny. Because of the transcription errors, it's basically predict a bleu score of 0. So which is completely useless, and Whisper Large is a bit better here. There are many other examples we can share here. And we also have the distribution, maybe interesting to look at the distribution. So this is the true distribution that you can see here. This is the distribution of the trend metric, and of course it's similar because basically we train it for this, so it can actually provide a distribution that is the right one. And you see the distribution obtained with ASR bleu using Whisper Tiny is not very similar to the initial distribution. It's getting better using a better ASR system. We start to see this B-modal distribution, but not quite as good as the initial one. So basically, this was maybe some examples I wanted to share. And again, this is preliminary. This is English only, so we need to move to multilingual. But we hope that at least this raised some concerns with the use of ASR bleu as a metric for target languages that are not equipped with very good ASR systems. So I think this is the main message, and probably learning metric is a good way to try to improve this thing.
Thank you so much, Laurent. Very and Ioan, two very interesting talks. Do you have any last question for Ioan and Laurent? Okay, so let's thank the speaker for the nice presentation. Thank you very much. I can stop the recording.
Thanks a lot for the invitation.
Thank you.
Thanks to you.